Hey everybody, we're going to mash up everything that we've learned so far and put work and energy together in what's called the work energy theorem. So notice here's our definition for work. It is a change in the energy of a system. So remember, energy, right? We just learned about kinetic energy, and so work is a difference or a change in that kinetic energy, okay? However much energy an object has is how much work it can do, and the amount of work done is equal to the amount of energy kind of given off or exchanged, okay? You'll see here that positive work means that energy is going in. You can think about that as gaining energy. Gaining energy, right? And so you can see that the speed increases. Let's use blue. Let's use blue for speed, for velocity. Okay, so your speed is going to go up. If you do negative work, energy is being released, or the object is losing energy. And so your speed is actually decreasing, right? It's losing speed. It's not going to go as fast, okay? So then here we go. Total work is equal to the change in kinetic energy. And here's the thing, right? Work is the change in kinetic energy, which is KF. I'm just going to make a little note of this, right? This is going to be KF. I don't know why there wasn't an F here. KF subtracted KI, okay? KF minus KI. What you'll notice is your masses stay the same. I'm going to put mass as, I guess I'm going to do mass as green. Oop. Your mass is green. Stop. Notice the mass is the same, right? What's different are the velocities. And that's what I want to show you here, right? Is there's a velocity initial and a velocity final. I'm going to go ahead and make sure that I write that F in there for velocity final. Okay, there we go. And you've learned that equation before, right? Kinetic energy is 1/2 mass times the velocity squared. So we also just want to remind you, like I'm a royal person, I want to remind you that Newton's law states, right, that the force that you exert on an object, that object also exerts the same amount of force, but in an opposite direction, okay? So work done by object 1 is opposite of work done by object 2. I just want to point out that this guy is negative, right? 1 is positive and 1 is negative. So example 1, how much work is done on a 10 kilogram object to accelerate it from rest to 100 meters per second? Well, we know that we have this mass of 10 kilograms. We also know we have two different velocities, from rest, which is 0 meters per second, to 100 meters per second. So how much work is done? Remember, work is equal to the change in kinetic energy, which we know is K final minus K initial. Okay, that's fine so far. Then, right, we know that K final minus K initial is, we're going to take 1/2, I guess I'm going to do it in purple, 1/2 of the mass times the times the final velocity, VF squared, minus, notice the 1/2 stays the same, the mass stays the same, but now we're going to do VI I squared. So the only thing that's really changing is the velocity, right? Your mass can't change. So what we're going to do is we're going to take 1/2 times the mass, and then in parentheses, we're going to have V final minus V initial and we're going to square that. Okay? That seems pretty easy. So let's plug in our numbers. We're going to take 1/2 times our mass, which is 10 kilograms, times, in parentheses, my final velocity is the 100 meters per second, minus my initial velocity is the 0 meters per second. And we're going to square it. So this is 1/2 of 10 is 5, then 5 times 100 squared, right? 100 squared. 100 squared is 4 zeros. So this is 50,000. Work is in joules, right? So 50,000 joules is my final answer.